So now we bring up the topic of extrema in these two variable functions. And so when we're talking about extrema in two variable functions, we're talking about these extremas on these surfaces. And the extrema are the same extrema that you've talked about before, in that, you're talking about maximums and minimums, and we can talk about local, or we can talk about absolute maximum minimums. Right now, we're really going to focus more on the local or relative extrema. And so here are a couple surfaces with a couple of points that we could look at as maximums or minimums. And so we look at, say, this point here and here. These ones would be your local minimum. Here would be your local maximums. I don't think this needs much explaining. We should all at this point understand that. There is this special point called a saddle point, which actually all three of these figures have. It would be sitting right here, here, or here, which is a maximum or minimum depending on the direction in which you're traveling on the surface. So let's look at the definition, then we'll go back and talk a little bit about saddle point, maximums, mins. So here, let f of xy be defined on a region R containing a point AB. F of AB, which is the z value, right, it's the function value, is a local maximum of f if f of AB is greater than f of x for all xy on an open disk centered around AB. All right, that's a lot of words, but what does it really mean? It means the same thing you think it means, in that if you're talking about this point right here being a maximum, okay, if I look at all the points around it on the surface, all the y values for all these points all the way around this thing, z values, are all smaller, all the function values for all the points all the way around it in an open disk around it are all smaller than the z value at this particular point here. So when we looked at this in Calc 1 and we talked about a maximum, we talked about it on a curve, okay? And so we had this maximum point here. And the way you did is you basically said, let's look to the left, let's look to the right. And if the y values immediately to the left and to the right of that y value were smaller, then this would be your maximum point relative to that location on the curve. Well, you can't just look to your left and to your right now at this point. What you need to do is you need to stand at the top of this peak here and look all the way around you, okay? And if every z value all the way around that point, all the function values all the way around that point are less than that function value, that z value that you're standing on, then that z value is a local maximum. And basically the same thing could be said for the minimum. F of AB is a local minimum of f if f of AB is less than all the other z values, the function values, all the way around in an open disk centered around AB. Same thing. Take this point, look all the way around you, and decide, are all the points around you sitting higher, have a higher z value than the z value you're standing on, in which case that z value right there is your local minimum. Now the difference there now with a saddle point is that if you're standing on this saddle point over here, and you look immediately this direction or this direction, those z values, those function values will be bigger. But if you look this direction and this direction, those are all lower than you. So depending on which way you travel, this way or this way, okay, that's what creates this saddle point. So this saddle point is both a maximum and a minimum kind of at the same time, depending on the direction that you're traveling, thus creating that saddle point. Right? So that's a special point. It's not an extrema necessarily, but it is a special point. So how are we going to find these extremas? Well, how do we do it in Calc 1? In Calc 1, we had to find the critical values. The critical values would then help lead us to the relative max and mins. Well, we're going to do the same thing here. In this case, though, we're going to call them critical points, because critical points are needed since our domain are x's and y's. There are points, right? The domain for these multivariable functions are points in the xy plane. So a point, AB, is considered to be a critical point of a function if the partial derivative at AB with respect to x and the partial derivative with respect to AB with respect to y equal 0. Or one of them doesn't exist. Okay? So when will both partial derivatives equal 0? The location of when those both partial derivatives equal 0 will be your critical point. Also, possibly, if one of these derivatives doesn't exist, that could also create another critical point. We focus more on the equal to 0 ones because we look at surfaces that have more continuity in them with the maximums right now. It's just a lot of examples we do. But don't forget, does not exist. Which is the same thing you talked about in Calc 1, right? The derivative equals 0, the derivative doesn't exist. But now we have two derivatives, and both have to equal 0 simultaneously, which will thus make us have to solve a system of equations in order to find critical points. And then these critical points should lead us to our local maximums and minimums, and possibly even saddle points. Okay, so here's an example where we need to find the critical points. It's something we need to get used to doing before we can move on to finding the actual extrema. So we first need to find the partial derivatives. So we have the partial derivative with respect to x. Should be easy to find. This is a simple polynomial function. So we're going to get 4x plus 8. This will be 0, this will be 0, this will be 0 in terms of x. Partial derivative with respect to y should be 2y minus 6. And we got to figure out when both of these simultaneously will equal 0. So then what we need to do is we need to solve 4x plus 8 equals 0 and 2y minus 6 equals 0. We need to solve that system. And so what we need to do is say, all right, well, this is pretty easy. This will equal 0 when x equals -2. This will equal 0 when y equals 3. Since neither of them has both x and y in it, then the point xy that will make both of these equal 0 simultaneously will be the point -2, 3. Because if I take that point and I plug it into the first equation, I really only need the x value because that's all that's needed in that equation, and it'll make it 0. If I also take that point and plug it into the second equation, the only thing I really need is a y, because that's all that's in that equation. It'll make that 0. So this point here is my only critical point. Now that was a very easy example. They're not all that easy. It was easy because the derivative with respect to x only had one variable in it. The derivative with respect to y only had one variable in it. But we know that that doesn't always happen. So let's look at the next example. Okay, so this one is going to be a little bit more involved, but still should be doable. But we will have both x's and y's in our partial derivatives in finding the critical points. And so if we look at the partial derivative with respect to x, that's going to give us y squared minus 2xy plus y. And the partial derivative with respect to y is going to give us 2xy minus x squared plus x. Now remember, both of these have to equal 0 simultaneously, or one of them could not exist. And we didn't talk about that in the last example, and we should have. We should also worry about when possibly one of these could not exist. But these are all polynomial functions. The derivatives are polynomials. The original function is polynomial. Same thing with the previous example. And so they're going to exist all the time for every x and y point in the domain. So not really an issue with these examples, but something you should think about in the future. And always worry about, okay, where the critical points could happen is when one of these could not exist. They have to equal 0 simultaneously, but they could not exist individually. All right. So we want to solve this system. We want to say, all right, let's look at this. We want to solve this system of y squared minus 2xy plus y equals 0 and 2xy minus x squared plus x equals 0. Now this isn't just a simple linear system of equations in two variables like you would have seen back in, say, like Algebra 1. It's a little more involved, but still just two variables. And there's two ways you would have done it with linear systems, which is substitution or elimination by addition. Elimination by addition doesn't work so well with nonlinear equations like these. So we're going to do more of a substitution, which is typically you take one of the equations, solve for one of the variables, then plug it into the other. And so we're going to use a variation of that here. So let's look at this first equation. First equation, what I can do is I can factor out a y, in which case I'm going to get y minus 2x plus 1 equals 0. And so now what do I have? I have two things multiplied together equal to 0. Zero product property says, well, either y equals 0 or this has to equal 0, which would give me y equals 2x minus 1. In which case I could then take each of those, which is solve for one of the variables, two different versions of y, but still what y equals, and I could take that and plug it in there. I could take that and plug it in there, the other equation, for y. In which case, if I use the first one, if I say, okay, let's let y equal 0, I would get 0 minus x squared plus x equals 0, in which case, I could factor out a minus x. I have x minus 1 equals 0, so x equals 0 and x equals 1, which basically tells me I have two critical points. 0, 0, x is 0, y is 0, and 1, 0. X is 1, y is 0. So I have two critical points, okay, out of that substitution. But I have another substitution that y could equal. So if I do that and I plug it in, I would get 2x times 2x minus 1 minus x squared plus x equals 0. In which case I'm going to get 4x squared minus 2x minus x squared plus x equals 0. That gives me what? 3x squared minus x equals 0. I could factor out the x, and I could get what? 3x minus 1 equals 0, so x equals 0 and x equals 1/3. Okay, in which case then what I would need to do is I would have to plug each of those now into my substitution, which would be this one right here. So if x equals 0, what's that going to give me? Well, y would be 2 times 0 minus 1, so negative 1. So 0, negative 1 is another critical point. And if I plug 1/3 in, I would get x equals 1/3. Then y would be 2/3 minus 1. So that would be what? Negative 1/3. So 1/3, negative 1/3 would be my other critical point. So essentially what I have here are 4 critical points for this problem. Now what I have to do is test. All right, well, are these maximums, minimums, saddle points, nothing? Well, that's where we're going to have to get to the next thing. The first part is make sure you can find your critical points. All right, then we bring up Fermat's theorem, which really looks a lot like the theorem we had back in Calc 1. It says if a function has a local maximum or minimum at a particular domain value, AB, then AB had to have been a critical point. What this does not say is that all critical points will give you a maximum minimum, but what it tells you is that the only places you could possibly have a maximum minimum would be at critical points, which is the same thing you said back in Calc 1. You saw that not every critical value actually yielded a local max or min, but the only places you could possibly have them were at those critical values. So the same thing is being said here. Okay? There are some cases where your critical point could yield a saddle point instead, which is not really an extrema, or it could yield nothing at all. Right? Sometimes you have a point. Think about it. In Calc 1, you had a curve that, say, did something like this, okay? And you looked at this point right here. This point right here has a derivative of 0. The slope right there is 0. The tangent line is horizontal. Yet that point is neither a maximum nor a minimum, but it is a critical point. But if you have a maximum or a minimum, say here or here, that has to occur at a critical point. The only place that could happen is if you had a critical point already. So max and minimums can only happen at critical points, but not every critical point will be an extrema. So how do we find them? Well, the way we're going to find them is by using what we call the second derivative test. In Calc 1, you had both the first derivative test and the second derivative test. And you could have used either one to find your extrema. Most students like the first derivative test where we talk about increasing and decreasing. That doesn't really work so well in 3 dimensions. Okay? Then you have the second derivative test, which honestly I like better in Calc 1 than the first derivative test, but most of the time you don't see students using it as much. But anyway, the second derivative test talks more about concavity and how you can use concavity to determine max and mins. And in a way, this is going to be used the same way here. It works a lot better in 3 dimensions. In order to do this, we need something called the discriminant, also called the Hessian. It's found by using all the second partial derivatives when you're calculating this discriminant. So what it is this big function here. Okay, so it's the second derivative with respect to x twice, second derivative with respect to y twice, and then the mixed partial are all in here. And really what it is the determinant of a matrix. So if I did this matrix here and I used all my partial derivatives, second derivatives, for a function. So we have xx, we have xy, we have yx, and we have yy. And I create a matrix and I find its determinant, which means I should multiply this times this minus this times this, would give me fxx times fyy minus these two multiplied together. But remember, these mixed partials should equal each other if the function is continuous. Okay? They should equal each other if the function is continuous. Well, no sense of talking about a maximum minimum point at a location where the function's not continuous anyway. So if these are the same, then I can say this is also xy, in which case then if I'm multiplying them together, it would be f of xy squared. And you see that's exactly what this discriminant is. And so we're going to need that as part of this second derivative test. So let's look at the second derivative test. So we're looking at a point AB that we've already determined as a critical point of f of x, y. We look at the second partial derivative, so xx, yy, xy. They all have to be continuous near AB. Okay? We all have to have these continuous. Then this f of AB, the z value, will be considered a local maximum if fxx is less than 0 and the discriminant is greater than 0. It will be a local minimum if fxx is greater than 0 and the discriminant is greater than 0. AB will be a saddle point if the discriminant is 0, regardless of what happens with fxx. If the discriminant is less than 0, automatically a saddle point. The big problem with the second derivative test is that it could be inconclusive when the discriminant equals 0. This is something you've seen in Calc 1. So in Calc 1, think about the second derivative test. Talked about concavity. I always like to kind of relate things back to things we've learned before. So you have concavity, concave down, concave up. Concave down, what happens? Your second derivative was negative. Concave up, your second derivative was positive. Okay? So this point right here would have already been found by finding the critical value by looking at the first derivative. Okay? Then what you did is you plugged it into the second derivative, and if you got a negative out of that, you knew you were on a concave down picture, which automatically gave you your maximum. This point, same idea. This would have already been found by finding your critical value, which is where the first derivative would equal 0 or doesn't exist. Then you plug it into the second derivative, and if you got a positive, it told you were on a concave up portion of the graph, and therefore you had a minimum. And at first it seemed kind of counterintuitive. A negative means a max, a positive means a min, but then when you thought about what that really means, a negative is concave down, and therefore if I'm turning down around this point, it should be a max, and a positive means concave up, and if I'm turning up around this point, then yeah, it should be a minimum. Then it started to make sense, but at first it was probably counterintuitive. But the problem was when the second derivative equaled 0, you didn't know whether you were here or here, and therefore it was inconclusive. Well, same thing kind of happens here. Think about it here. Local maximum if the second derivative is negative, local minimum if the second derivative is positive. All right, that's all determined as long as the discriminant is positive as well. And then also that we have this inconclusive component about when discriminant equals 0. So a lot of correlations between your second derivative test in Calc 1 and now. But nonetheless, this is your second derivative test. Okay? So we look at the second derivative test and we determine if we have a max or a min by doing that. First, we have to find the critical points by looking at the first derivative. Then we plug them into the discriminant and the second derivative with respect to x, and we can determine what happens from there. So here's the first example we did. We've already determined that the critical point, there's only one of them, is negative 2, 3. That was the critical point we found. And so what we need to do is we need to look at now the second derivatives so that we can determine whether or not that critical point is in fact a max or min, saddle point, or maybe nothing. Okay, maybe we won't be able to do anything here. And so in which case we need our partial derivative with respect to x and y first. Then we can do our seconds from there. So remember, x was 4x plus 8, y was 2y minus 6, fxx is going to be 4, fyy is going to be 2, fxy is going to be 0. So my discriminant in terms of x and y is going to be 4 times 2 minus 0. Since all these are constants, it's actually just a constant. It's 8. That is positive. Regardless of what point I use, it's always going to be 8. It's a constant function. So the discriminant is positive. All right. So that right there is a starting point. So now we got to look at the fxx. So if I find fxx at negative 2, 3, what am I going to get? If I plug negative 2, 3 into fxx, well, it's a constant. It's just 4. Okay? So no matter what I plug in, I'm going to get 4, which is positive. So fxx is greater than 0. The discriminant is greater than 0. Therefore, negative 2, 3 is a local minimum. That's it. Okay, pretty easy. Okay, we should be able to handle that. So this is the other one we already did. We already found the critical points. Those critical points were 0, 0, 1, 0, 0, negative 1, and 1/3, negative 1/3. Okay? So we have to test them. So we need our partial derivatives, with respect to x, which was, what was that? It was y squared minus xy, or 2xy plus y. And derivative with respect to y was y squared. Oh, nope. It was 2xy minus x squared plus x. Then we need our second derivative with respect to x, y, and the mixed xy. So we look at each one of these, and we say, all right, well, what do we got? xx. xx will be simply minus 2y. yy will be 2x. xy, which is this, but now with respect to y, is going to be 2y minus 2x plus 1. And then we need the discriminant, which would be this times this. So it would be minus 4xy minus this squared. So 2y minus 2x plus 1 squared. Okay? And so now we need to test each one of these points. So let's look at 0, 0. So 0, 0. I always like to look at the discriminant first, and then I'll look at xx. Because if the discriminant is negative or 0, this xx doesn't matter. If the discriminant is positive, then I'll look at what happens with fxx. So 0, 0 into the discriminant. So if you think about this, it'll be 0 for sure. This will be minus 1 squared. So that'll be negative 1, which is negative. All right, well, the second the discriminant is negative, what do we say? We said that 0, 0 has to be a saddle point. All right, let's look at the next one. 1, 0. We'll look at the discriminant at 1, 0. fxx possibly at 1, 0 if we need to. Well, if we plug it in, the first piece is going to be 0 minus, we plug into the second one, we're going to get, 0 minus 2 plus 1, so that'd be minus 1 squared. So it's still going to be negative 1, so that's less than 0. All right, we don't have to bother with this, so that tells us that 1, 0 is a saddle. All right, let's look at 0, negative 1. So look at it in the discriminant. Let's see what happens. We're going to get 0 again. Y is negative 1 this time, so we're going to get minus negative 2 plus 1 squared. Again, we're going to get negative 1, which is less than 0. So this one's a saddle point also. All right, finally, let's look at 1/3 and negative 1/3. I don't think this is a saddle point. So look at the discriminant for 1/3 minus 1/3. Okay, so we plug it in here. What are we going to get? You're going to get 4/9 minus, plug it in here. So we'll get what? This will be minus 1/3 squared, so 1/9. So that's definitely positive. So now we'll look at fxx at 1/3, negative 1/3. And when I plug it in there, I want to get what? 2/3. So that's positive. So that tells me I have a minimum. Okay? So there's a minimum. There's a saddle point. This one is also a saddle point. And this one's a saddle point. So 3 saddles and a minimum. If we take a look at what the graph would be, we can clearly see all this stuff happening. So here's both the 3D model and the level curves version of this surface that we just looked at. And you can see where these 3 red dots are. These are your 3 saddle points. It's a little hard to see in a 3D image, but you see you can go this way or this way, and you have kind of your max and min. Same thing's happening here and here. It's easier to see in the level curves that you see kind of this crisscross pattern here, here, and here is where you have your saddle points. So if I go this way versus if I go this way, max or min, same thing kind of here. If I go here versus here, or here versus here. And then we had that minimum point at 1/3 minus 1/3, which basically sits right kind of in the middle of this triangle, which would be sitting right about here in this indentation, which is where I'm going to end up hitting this little minimum point before it starts coming up kind of in all directions around this point. So everything around that point has a higher z value than that point right there, but that's where your minimum would sit. And you see this just verifies all the things we just did computationally, but you can see it in these models, either the 3D model or the level curves. And I think the level curves kind of does a better job of doing justice to seeing where all these saddle points and the minimums are. So now here's an example where we'll do it all together at once. So we need to find the critical points, then test them, and determine if we have a maximum or minimum. And so let's look at this one here. We need to find first our first derivatives. So derivative with respect to x is going to be 3x squared minus y. Derivative with respect to y is going to be minus x plus 3y squared. While we're at it, we might as well find our second derivatives as well, because we're going to need those. So let's look at all our second derivatives. So xx will give us 6x. xy will give us what? Minus 1. And yy will give us 6y. So then our discriminant will end up being 36xy minus negative 1 squared, so minus 1. All right, so now we first look at where each of these will equal 0 together. That's the first part. That'll give us our critical points. We solve that system. That's pretty easy to do. If we look at this first equation, we could solve it for y. Y equals 3x squared. In which case, then I could plug that into the second equation. So that would give me minus x plus 3 times 3x squared equals 0. Okay, then I'm going to solve that for x. So what do I have? I have minus x plus 9x squared. No, I made a mistake here. Because this is y is being squared, so this is y. So therefore it should be squared. So what I'm going to get here is 3x squared would be 9x to the 4th times another 3 would be 27x to the 4th equals 0. So if I factor out what a x, I'm left with 27x cubed minus 1. So this will give me x equals 0 and x equals the cube root of 127, so 1/3. So I have two x's. Each of those then have to go back to where it came from, which is here. So if x equals 0, we're going to get y equals 0. If x equals 1/3 in here, we're going to get y to be 1/3 squared is 1/9 times 3 would be 1/3. So I have two critical points, 0, 0, and 1/3, 1/3. So now I'm going to test each of those. So let's look at 0, 0. So I'm going to find the discriminant at 0, 0. So that's going to give me 0 minus 1, so negative 1, that's negative. So then we have a saddle point there. All right, then I'm going to look at 1/3, 1/3. And I'm going to plug that into the discriminant. In which case I'm going to get 36 over 9 minus 1, that's positive. So then I have to plug it into xx. And if this is xx, I'm going to get 6 times 1/3, which is also positive. So that tells me that this is a minimum. Oops, minimum. So I have a minimum here, and I have a saddle point here. Again, we can verify this by looking at the graph. Okay, so again, we can look at it two different ways. We can look at it in the 3D model or the level. I think the level curves is easier. So if we look at 0, 0, that would be right there. Then if we look at, say, 1/3, 1/3, which would fall right about here, these are where we're going to have our 2 points. This one we said was a saddle. And you can see if we go this way or this way, it's kind of where your saddle's going. Here you're going to be increasing or decreasing. And here's where your minimum sits. If you look at it right in here, 0, 0 would sit right about here. And the minimum point is kind of right about there. So if you travel this way or you travel over this way, that's kind of where you're seeing your little hint of a saddle. And there's a little dip in the surface right about there, which is where we're going to hit that that minimum point. All right, so again, clearly you can see it through the two graphs, whether you use the 3D model or the level curves, you see that verifying the computation that we've already done. All right, so this one we're going to go start to finish, find our critical points, test them, and determine whether we have extrema or saddle points. So let's look at fx and fy first, and then go from there. So we already got 4x cubed minus 4y, then 4y cubed minus 4x. Fxx would give me, what, 12x squared. Fyy would give me 12y squared. And fxy would give me minus 4. Your discriminant would be this times this, so 144 x squared y squared minus this squared would give me 16. So then we look at when each of these is going to equal 0 at the same time. So it doesn't matter, pick one. I'll solve this one for y. So if I did that, I would get y equals x cubed. And I'll take that and I'll plug it into here. So that's going to give me 4 times y, which is x cubed cubed minus 4x equals 0. Okay, so that gives me 4x to the 9th minus 4x equals 0. Factor out a 4x, I get x to the 8th minus 1. So this will give me x equals 0. And since this is an even power, that's going to give me x equals plus or minus 1. So I have 3 different x's. All have to go into this y to figure out what y then equals. Finish this off, I'm going to get 0, 0 as 1 point. Then I'm going to get 1, 1, and then -1, -1. Again, plug 0 in here, I'm going to get 0 for y. Plug 1 in for x, you're going to get 1 for y. Plug -1 in for x, you're going to get -1 for y. So I got 3 critical points. So let's test all of them. Let's look at the discriminant at 0, 0. We'll look at the discriminant at 1, 1. And the discriminant at -1, -1. And then if we have to, we'll look at fxx. So 0, 0 for the discriminant, that's going to give me -16. Oops, -16, let's write it there. That's negative. So that tells me that 0, 0 is a saddle point again. All right, let's look at 1, 1. Plug 1, 1 in, you get 144 minus 16. That's clearly positive. So now I do have to look at fxx. So what am I going to get here? I'm going to get 12, which is also positive. So that tells me that 1, 1 is a minimum. All right, so that one's done. Then -1, -1 into the discriminant would give me the same thing, 144 minus 16. So that's positive. So now I'll look at fxx at -1, -1. And fxx is going to give me 12, which is positive. So that's going to give me another min at -1, -1. So I got a saddle and 2 mins now in this particular one. Again, computationally not overly difficult. A lot of algebra here. But we test them with our second derivative test, looking at the discriminant and then fxx, and then determining whether we have a saddle point or a min. Again, we can finally verify this by looking at the graph, and once we do that, you'll see you get the same thing that we just got computationally. So you see we had 2 minimums and a saddle. So your minimums are going to sit here, and your saddle's sitting right about there. Okay, so you look, you kind of go over, there's a little bump here, you can kind of go this way, and you have your little indentations here. Again, easier to see in the level curves. There's your 2 minimum points, and your saddle point sitting right here. Remember, the saddle point was at 0, 0. This was going to be -1, -1, and this one was +1, +1. Okay, so you see minimum, minimum, saddle point. It's a little harder to see the saddle point here, but basically the idea is if I go this way versus if I go this way, I can create that maximum or minimum. So I have a little hump sitting right here if I go this way, but it also is an indentation if I go the other way. All right, so again, verifying through our computation in the graphs that we had the 2 minimums and the saddle point.